Yeah, you guys are exhausted, huh?
Yeah.
Got you wiped out. This can't be my class, can it? Our class, sorry, our class.
Definitely a huge factor.
It better be. isn't it? All right, remember to smile. We are recording today.
Does it give me the video?
Huh?
Am I video?
Yeah, I think so.
Is it on that?
It's basically review and yeah. Hey, so welcome to class. Kevin, you mind closing the door, please? And then if you could, actually leave the lights the way they are. Today we're going to continue with our review. The thing that we didn't get into was nitrogen, right? We didn't get down to the nitrogen cycle, the biogeochemical cycles. And that's an important one to consider because today I'm hoping that we'll get to talk about eutrophication a little bit. We may get to secession, maybe. I think we've talked about it a little bit. And feedback loops. Those concepts are really, really important.
If we don't talk about it, we'll be on the test.
Yeah. They'll be on the test regardless. Yeah, so test is on 4 and 5, and I'm hoping that we'll have some time for review. It is a multiple choice test, so the setup is similar. If you wanted an essay, we can talk about an essay. If I do an essay, it would be about the pond, and it'd include the data similar to what you got out of the pond, and you just have to interpret that. Just let that one sit. I heard saw a lot of reactions quickly. But let it sink for a minute. I don't care either way. So what we need to do is talk about nitrogen. So we had Legos and things last time where we were looking at that kind of stuff. In the interest of time, I think we're just going to talk, unless you feel like seeing those materials are really good. I think it's better for the people who are manipulating it. Do we feel like we understand the carbon cycle? What's the main source of carbon? Fossil fuels with humans. What's the source of it naturally, without humans pulling it out of the ground? Where do we find all the CO2? In the atmosphere, right. Can you, right now, do a pathway where you can go to 3 different stops as a carbon atom? Start in the atmosphere. Let's do it. Where do we go? What?
Trees for photosynthesis.
It should go to a plant first. CO2 is gobbled up by plants, so we're going to use tree first. Goes into a tree. Now what? It's in the tree.
Consumer eating the tree.
Consumer eats the tree. Let's be specific. What consumer?
A deer.
A deer. I was looking at Will. He represents a giraffe. Hoping he'd chime in. So deer eats a leaf. Goes inside the deer. It's in there. Poops it out. Okay.
Or breathes it out.
Or breathes it out. Which direction are we going?
Breathe.
Yeah,
Let's go with respiration. Breathe it out. Okay, so now it's out in the atmosphere again. 1, 2, 3, 4. This is 4th stop. 2 more stops. Now where?
Ocean.
How's it get in the ocean? It can mix or
Absorption.
how?
The plankton.
Through photosynthesis. But the waves are going to probably interact with it and things, and so soaks it up. So it gets brought. The CO2 gets brought into the water, and then it's used in a photosynthetic plankton. Now what?
They die and decompose in the sediments.
And stay in the sediment in over a million years, possibly. Right? Nice. Feel like you do that in a multiple choice setting? If I gave you a graph, you fill it in the blank spots, A, B, C, D, E selection? Winnable? Losable? It's more like Bridgeton against Proctor, right? So we're going to whoop them. We don't care what kind of jail they're from. Right? These guys are like full-on prison guards, right?
Yeah,
They have the stripes.
I was literally saying like, oh, you guys are fine. You probably just go enjoy a beer after the game, anyways.
They're probably, some of them look like they already enjoyed one.
They're
Yeah,
all
whoop
good,
them.
like 21, 22.
Whoop them.
Wait,
I'm proud of you guys. Okay, yes, back to
how
business.
many questions?
50 at
So
the
same,
most.
same length as last
Yeah.
time.
Yeah.
And so there's gonna be graphs like with carbon and those things. And
Yes.
you fill in.
Yeah. or maybe a description, and you say what the next step would be. Yeah, you feel winnable?
What?
Does that feel winnable?
I don't know, we'll see.
We'll see. Okay, let's get a place where we feel like it's good. Let's talk about the other, oh, okay,
If we had an essay, would there be less question?
yeah.
I think we should keep it to multiple choice.
So let's talk about,
Definitely.
so phosphates, we understand where phosphates come from. What's the source for phosphates?
Rock.
Rock. And how does it move from there? Can you do
Water erosion.
water erosion, then what?
Goes
Soil.
into the oceans.
Goes in oceans or soil?
Yeah, and then plants pick it up.
Plants can pick it up. How does it get picked up in the ocean?
Through the aquatic.
Aquatic plants or phytoplankton? Right, anything photosynthesizing. Good. And then we usual paths after that, just like carbon. So nitrogen's really the tough one. Nitrogen is the tough one. So I'm going to go to a diagram, and then you guys have worked on nitrogen. You are going to explain it. Look at it more, right? Because you're in that crew, right? That was you.
This is on.
Who else? Who else is in the crew? Okay, okay, nitrogen. We're getting ready to go. So nitrogen. What is our source for nitrogen?
Atmosphere.
Atmosphere. How much of nitrogen is it? How much of the atmosphere is comprised of nitrogen?
78%.
78%. Wow. Just hanging out in nitrogen. All right, so how does it, well, let me go to the diagram. Well, actually, yes, tell me, what happens? How do we get it into a plant? Will, what do you think? If you don't remember, that's fine, too. What do you think?
Does the plant absorb it?
It does absorb it, but it cannot absorb nitrogen gas. It has to be transformed. Or in this case, the word is fixed. And it's not through photosynthesis.
Bacteria.
It's through a bacteria that is nitrogen fixing. So bacteria is kind of like the chef. You know, if you're a chef, you're taking raw materials and you're cutting them up and you're cooking them into a sauce, or you're cooking them up into a casserole or whatever. That's essentially what this bacteria is doing. It's taking a raw resource into nitrogen gas, it's pulling it in, and what is it fixing it into, Ben Charleston?
NO3.
Can fix it into NO3. So it's putting 3 oxygen atoms, bonding it together and letting it out. And plants then soak it up. How do plants take in NO3? Through their roots. That's right. What's another way that they can fix nitrogen besides NO3? There's 2 other forms. I'm talking about the molecules. Yeah, lightning will shortcut it into NO2. So nitrates and nitrates are what we're talking about now. NO3 and NO2. Right? What's the other one? What's the third one? NH4. What is that? Say what? Not methane. Yeah, that's CH4. NH4 is ammonia. So nitrogen-fixing bacteria, there's different species that do those jobs. And it's just fixing the bacteria into a new form that can be taken up by the root systems of plants. I don't know why my screen mirroring is not working. Let's try this again. Something must be wrong. I was going to show you a diagram that's really handy. So, once it's absorbed into a plant, then what happens to the nitrogen in the plant? Something eats the plant. The nitrogen moves on to that consumer. What happens? Let's get the nitrogen back in the atmosphere. How does it get back in the atmosphere?
Waste?
Yeah, animal pees or poops. Can't connect. It's weird. Peas or poops, and then we have bacteria that changes it again to the gas.
So both times when it goes from nitrogen to something that plant can consume, the waste to,
Whenever you're moving from a gas to a fixed state, to a fixed molecule, from a nitrogen gas to a new molecule, nitrogen molecule, it has to be fixed by bacteria. So when it comes out of the atmosphere, it's fixed into a new form, and when it goes back into nitrogen gas, it has to be fixed by bacteria. So the most important agent in the cycle is?
bacteria.
Got it. That'll be a multiple choice question, Zach. Okay? Yeah. For nitrogen. I want to show you how it happens when it breaks, because this is the most important part. But the airplane's not working. Airplane! All right, let me just try it. I gotta try this. So while I'm trying to get this to work, I want you to do something for me.
When the bacteria fixes the nitrogen, what form does it turn into for the plant to be able to?
NO2, NO3, or NH4. Nitrates, nitrites, and ammonium. Now, for some reason, I can't remember which was nitrate and nitrite, which one it is. I won't be testing you on the difference, but I can't remember which one's which. And there's the difference of one oxygen. I can't remember. All right, I'm trying to get this airplane thing to work. I'm going to try one more time. Turn it on and off a couple things. See if I can have some better results. Wireless is working, so it's not that. Let me try one more time. So while I'm trying this is what you should do. You're going to use your own screen, because if this fails, I need you to be on screen to see what eutrophication is all about. So we're going to go to chapter 5 notes in that topics page on ecosystems. Please go there. Oh, look at that. I've gotten lucky. And I'm going to show you one of the most important slides for this test and for our understanding as it relates to our studies. This is like my Harry Potter wand. So we're going to look at hypoxic zones, dead zones. And some of you know all about this. I'm mainly looking at Will and Joey. Did you learn all about this on Ocean, right? You guys went on Ocean, right? Right? And whether you remember it exactly or not isn't the issue. It's just knowing it as a whole that matters. So this slide right here is going to be the most important slide out of this chapter. Can you see it okay from where you're sitting? I know the video watchers can't see it, but it's slide number 18.
What is chapter 5 under again?
It's the picture of the kids gardening.
Okay.
And it'll be in the top corner. That's where the notes are. In a PDF form. So you can print this up if you want and study. But these steps are vital. So in this case study, the opening study of this chapter is about the oyster beds dying off due to over-harvesting and the pollution. We talked about this a little bit already. And the pollution is due to all this runoff from synthetic fertilizers that have accumulated in the watershed, moved down the watershed, similar to the watershed of Blackwater River. Imagine if we were polluting along the way of that thing all the way down to where it dumps out in Boston. Same idea. So these steps that happen is we have this reaction to this excess of nutrients. So I'm going to write a couple notes on here that are really important before you get into these steps. So the way this pollution is entering the system, the marine system, this is happening in marine. This can happen in freshwater and marine environments, but most of the most significant dead zones are found off the coasts. Let's see, let me go to the right picture. Off the coast of our planet. So right, oh my gosh, right there. We have 500 different dead zones. Look at all those along the East Coast. Wherever our waterways are draining into the ocean, there's this inordinate amount of pollution and it creates dead zones. And we're going to understand what that actually is by going all the way back to
So
this
this-
side.
This slide is about hypoxia, that like.
Yes, hypoxia is the result of this process called eutrophication. So this is the steps to eutrophication, to write it down the bottom. Notice it has the word trophic in it, that means feeding. Eutrophication. And this is that results in a low oxygen environment, which kills off the ecosystem, like that. Kills off the community. So what's happening is we have this runoff of macronutrients. And the macronutrients that we are concerned about here are nitrogen and phosphorus. They're called macronutrients because all life forms need these in large amounts. You need lots of nitrogen and phosphorus in your diet in order to be human, or to just be alive. All organisms need large amounts of nitrogen and phosphates in order to live because gigantic molecules that operate your system require them structurally, just like carbon. We're all made of carbon. All living things are made of carbon, like this tree that is now a table. This is a carbon skeleton that holds this tissue together and makes us able to use this. You are made of carbon too. If I was to take carbon out of your body, you would not exist. You'd be vaporized. So with phosphates and nitrogen, it's similar. So what are some of the big molecules in the human body that require or are built by phosphates or phosphorus, have phosphorus in them? Remember,
Aren't cell membranes?
yes, all cell membranes, because they're phospholipid bilayers. I'm going to give you this to Sarah later. That was awesome. Should be proud of you.
Sweet.
Sponge, remember sponge. These things are macronutrients. You need lots of these to operate. So phosphorus is required for all cells, every single one of them. What else do we find phosphate or phosphorus in?
DNA.
DNA, every DNA strand, the ladder to DNA that twists, structurally is a sugar molecule and a phosphate. Take phosphates out of that, no life, no code of life. Okay? ATP, adenine triphosphate, that is a molecule that has phosphate in it, and that helps things react inside of bodies. Inside of cells, sorry. All cells. And remember, all living things are made of cells. So all living things need phosphate. Nitrogen. How about the same thing with nitrogen? Where do you find nitrogen? Yeah,
Amino acids.
amino acids. Amino acids make up
Proteins.
all proteins. Examples of proteins would be chicken, so meat, muscle. Your muscle fibers are all protein. Your hair have less protein over here. What else does protein do? Functionally. We talked about saliva already? No?
All of them make N.
Yes, they're enzymes. So like in your mouth right now, you have saliva, and it has an enzyme in it called salivatory amylase, and it breaks down carbohydrates. And that's why you would put something like a saltine in your mouth, it'll start to dissolve, and you'll taste the sweet taste of those sugars and that carbohydrate. Pretty cool. So enzymes are doing all that. They're also allowing you to think, hear, pay attention, or have an imagination. So it's good stuff. So we need them. That's why they're macronutrients. All life needs nitrogen and phosphates. So we use them. The problem is we use them on synthetic fertilizers. We talked about this, right? We talked about synthetic fertilizers, yes? Yes. So synthetic fertilizers are dense in N and P and K, and those nutrients. Potassium's not one of our macronutrients to worry about, but N and P are. They're the ones that are of importance here. So they're running off the fields and croplands and getting into the water. So that's our first step here. Step one, nitrogen and phosphorus input. In order to solve this problem, we have to fix that part. If we ever want to stop eutrophic events occurring on the planet, dead zones, if we ever want to stop dead zones on the planet, we have to address where the nitrogen and phosphates are coming from. Typically, it's agriculture.
So it's the synthetic fertilizers that are the runoff that's going down?
They are the culprit that has the most nitrogen phosphates in them. Now, we'll have rain events that will flood out lagoons that hold pig waste or poultry waste or human waste and get them into the waterway. So all these hurricanes we've had in North Carolina, Florida, etc., they'll result in these huge influxes of nitrogen and phosphates into the system. One of the reasons why you should never swim in flooded areas. They're filled with feces.
When you say dead zone, what do you mean? Is
We'll
it-
get there.
Okay.
Let me get there, because that's the last stop. But yeah, it means that there's biodiversity.
This one, yeah.
All right, so our first step is that input comes in, and it's gathering as it comes down the watershed, more and more. There's so much of it, and when so one of the most important statements we're going to make about our natural systems is in a natural system, all waste equals food. Nothing is wasted on this planet. All nutrients are recycled. They're useful for something. All waste is food for something. Think about it. When that deer dies in the forest, it becomes food for some other animal, some decomposer, some detritivore, eventually some plant. Remember we talked about the circle of life and the circle of poo. Mufasa says to Simba, we rule over everything, but we give our bodies back and they become grass. All flesh is grass. That's what it said in Omnivore's Dilemma too. It's a cycle. Right? Recyclable cycle. All waste becomes food. And we also know that a lot of food equals sex or reproduction. Right? Keep those in mind here. So we go to step 2, highlighting step 2. Phytoplankton flourishes at the surface. So here's all the phytoplankton at the surface there. That also includes algae. It's all sitting on the surface. There's all this new nitrogen, potassium. Yay, extra food. That means let's reproduce. We're going to make more of each other. Yes, yes, yes. Right? And it spreads. It gets bigger and bigger. What's going to happen now? Now that there's more algae and phytoplankton, they're now starting to compete. What are they competing over? A limiting factor, right? What? No, they're making oxygen. Remember, they're photosynthetic critters. What are they competing for? Sunlight, layer by layer. The ones that don't get enough die and drift to the bottom. What kind of competition is this between algae? Intra-specific competition is occurring, right? And sometimes that results in death. Let's spell competition wrong. Right? Or it could be interspecific as between the phytoplankton and algae. So the ones that lose, like Bridgeton, die. They get shut down and they go home wet and upset. 2 years in a row. So look, you look at step 3, dead phytoplankton and their waste drift to the bottom. They die. But we know that waste is food. Dead bodies is food. Dead man's party happening at the bottom. Who's going to flourish now? Decomposers or detritivores. Detritivores like crayfish. Detritivores like mayflies. Detritivores like a lot of other things. So that means if they have a lot of food, they're going to reproduce. There's going to be more of them. That's true for bacteria too. They're going to start reproducing. Lots of food, yes. Things are good. Let's multiply. Exponential growth. No limiting factor. Let's go. Let's get crazy. That's what nature does. That's what humans do too. If there's no limits to access to resources, we act in our own self-interest and we eat it all. So in step 4 now, right here, you follow me. So the decomposer, if they're growing, they're running out of something that's vital. They now have a new limiting factor because the algae and phytoplankton are so dense on top. What has happened? What's happened? What do decomposers need if they live in the water in order to survive? Oxygen. Dissolved oxygen. Mayflies need a certain rate. dissolved oxygen levels are starting to fall. Why?
Because there's more of that population that needs the oxygen.
All the populations above.
Okay, say it again, Michael, then Chris.
There's more of that species that needs the oxygen because there's so much food.
Yeah, so they're eating up all the oxygen. But something should be making oxygen. What's happening with that? Chris?
They're all above.
They're all above. And they're blocking out the plants at the bottom. See the grasses at the bottom in the figure? They're not getting what?
Sunlight.
You're not getting sunlight. Turbidity has increased, right? Remember that? So turbidity is increased. That means that NPP is higher or lower. What should NPP be doing? It's going to be lower. And that means there's lower dissolved oxygen too. So what does that mean for the decomposer population? El muerto. Boom!
Dead zone.
Dead zone. That's right. They consume more and more oxygen until there's none left. There's no new oxygen being made. They're gobbling up all the available oxygen. Dead zone. When a dead zone forms, things that need dissolved oxygen cannot live and stay there. They leave. So that zone becomes devoid of life. There might be a few stragglers, really tough species that don't require dissolved oxygen living there, but for the most part they're gone. What would be an example of an animal in a freshwater environment that doesn't need dissolved oxygen, gets oxygen from the surface that can survive in this dead zone?
Frog.
A frog. A what? A dolphin in a marine. Okay, good. These are air-breathing creatures. Don't need that stuff. Back swimmer, water boatman, those things we saw in the pond, they don't need dissolved oxygen. That's why they were never ranked as a sensitive critter. Okay, so you see how that can be detrimental? How do we solve this problem?
Stop putting fertilizers.
We have to stop the inputs. So fortunately with agriculture we have growing seasons. We have sometimes where it shuts down. So some of these dead zones grow large in the growing season and shrink down to smaller or non-existent sizes. Some of them stay all year because it's based off of feedlots, things like that. Pretty crazy. So that's it. That is a process of eutrophication. If I gave you this process out of order, could you reassemble it in order?
Yeah.
If that was the case, how would you prepare for that on a study day? Stare at this until it makes sense?
Yeah.
No.
Write the steps over and over again.
Write the steps down unnumbered on separate index cards. Shuffle and put in order. That's how you do it. Or you do it digitally on a Quizlet kind of setup. You have to arrange it in the right order. Test yourself that way. I have this on the test. I know we were just now talking about it. You should have read about it a while ago. But I don't think that this is so complicated of a... I think you can get it. Yeah. Yeah, if anybody else wants to take a picture of this, you can. Then I'm going to show you the impacts of it. In fact, we have this event happening right now in America. Anybody know where it's happening? It's affecting Michael Hughes' animal a lot, which is kind of strange, because you wouldn't think it would affect the dog, but it is.
There's no food.
Say what?
They don't have food, right?
That's right, it's related to food, but it's worse. It's worse, it's more. Yes. Where are we talking about? Does anybody know where there's a eutrophic event happening right now that is making the headlines?
Florida.
Right. The Carolinas, there will be, from the flooding, there should be one, but the big one right now is in Florida. I'm going to shift to that article if I may. We're good with this? We'll come back to it. So I'm shifting to that real quick. Boom, and right here. So these are images of a red tide events. So red tide is an algae that is caused by the same process as a eutrophic event. It's caused by the inputs, the excess inputs of nitrogen phosphates. And this is a particular species or strain of algae. It's called red tide, and it is bad because not only does it do the things that we just described, it also has environmental health issues. Does anybody know what they are? This affects your species as well, Zach, as you might imagine. Yes, what is it? Yes, they're toxic. And so it is releasing, some of these organisms will go into a cyst-like state or it'll produce some gases that if you inhale it, you get ill. In North Carolina, there's been these outbreaks of hysteria, which is similar to eutrophic stuff. It's a type of, it's not algae, but it's a protist that can go from a dinoflagellate stage to an amoeba stage to a cyst stage. When it's in a cyst stage, you can inhale it, and then it'll go into your brain as an amoeba and eat holes in your brain. You'll lose memory loss, maybe even death. Permanent brain damage. Discovered by a North Carolina State University chemist who ended up dying from overexposure to it as well. Crazy stuff. Eats flesh.
And that's just
in
hanging
fish.
out in the water.
Red tide.
This isn't red tide, this is hysteria that I'm talking about right now. But it increases in population when it has extra nutrients from sewage, specifically pig sewage, so a lot of nitrogen and phosphates. Similar to this, but it has to be the right conditions for it to be deadly. Just like this red tide, which can be deadly too. Here's some of the results. Why are the fish dead? No oxygen.
Why are their eyes so full of people?
It might be just the way they're as a species, I don't know. There's a puffer fish right there. Two-wheel puffer fish. Sorry, buddy. There's a catfish right there. Something like it. It's all sea stuff. So red tide, you can kind of see the tide, the coloration of the water there. Some more. And so when these events affect a lot of things, not only is it ecologically problematic, it's also socially problematic due to the health issue. What about economics? How does this affect economics of these regions?
Costs a lot of money to fix it.
Costs a lot of money to clean it up, absolutely. What else?
Fishing.
It hurts the fishing industry. Can't really eat or sell fish or catch any live fish with this event. What else?
People might not visit that area.
People don't want to visit places that can kill them. You know, make them really sick. We don't let people swim in water like this because it is an increased risk to their health. It's a health concern. And so one of the issues has been right there. Sorry, Michael. It's for your peeps. Dolphins have been dying. Why are they dying?
No food.
Part of it's no food, but
Infected fish.
they either might eat infected fish or they get exposed to the toxic algae, and it increases their chance to get a disease, lowers their immune system, or it affects them directly. I don't know enough about these red tide things to know exactly what it's doing, but often in the headlines there increased disease outbreaks due to red tide. And it's been happening for a while now. I think it's been happening off and on for almost a year in Florida. The main culprit isn't just agriculture, it's also sewage treatment. Some sort of sewage treatment issue is not working right. They're not processing the nitrogen and phosphates well enough to protect the environment and people. So I say fire those people. That's my opinion. And that may not be the only way you solve it. All right, so that's eutrophication. That's how it works with big scale. Let's see. Let me show you one other picture. There's another look at what it looks like. You can see which side is eutrophic and what isn't. And so if you were an environmental scientist and you're set upon this, Somebody asks you, solve this problem, what's the first thing you're gonna do?
Maybe agriculture.
You look at agriculture and look at where sewage may be running off. And it doesn't have to be just human sewage, again, it's agriculture. Good. Questions about this?
So when you were talking about the way to fix it, you said just, so decrease the amount of phosphates, nitrates that are going.
You have to address the root cause. What's causing the eutrophication? Increased inputs of nitrogen and phosphates. If you go upstream, you'll find it. Yes?
Shouldn't the like top part of the water at least stay oxygenated?
Yes, but it doesn't often mix. So I'll show you one of the other images. So like here's an image here with the red tide event. You can see they're pointing out where these events are occurring, but the currents are not allowing it to mix enough. And typically the inputs are at mouths of rivers. It's not extending way out into the deepest, darkest parts of the ocean. It's usually within a mile of the mouth of the river where the water is flowing in one direction, right? So that the inputs are flowing in and then it dissipates and goes further out. And then if you don't have the right current, it may bloom big. Good? Okay. Let's talk about one other concept. How are we doing on time? Doing good, okay. One more concept, and then we'll review as a whole. So, one of the biggest concepts that we've talked about in this class is living systems versus mechanical systems, right? Living systems can self-repair, self-organize, because they have interrelationships with other living components. So up here in this chapter, it defines a system. We already knew this, that it's interacting with its parts and has a dynamic relationship with those parts. Like your eye and your brain, or your ear and your brain right now, you can hear me. They interact and influence one another. And so with that, your body reacts to inputs. For example, the temperature in this room is an input. It is creating your body is creating an equilibrium to deal with this environment. If I was to make it cold in here, I was to open all the windows and make Will stand at the window, he would eventually get cold. So his body temperature is going to start to fall. But his body is not going to allow that to happen because it interacts and influences other parts. How is his body going to react? He's going to start to shiver. What else may happen besides shivering? Goosebumps. Goosebumps, what's the point of goosebumps?
Doesn't it make your skin like thicker? Like,
It's a vestigial reaction.
isn't it
It's,
just, it's where you used to have like hairs and then.
yes, it's a vestigial structure. Our evolution, since we're descended from primates that are hair covered, fur covered, we're not so fur covered, we're hair covered. And so the goosebumps creates pillowing, which spreads out hair or feathers to get more air trapped in between the hairs, so the heat from the skin and that air heat up and create an insulating layer, pillowing. And it's a reaction for pillowing, which doesn't work at all. That's a reaction. So instead we shiver. What happens when you start to shiver? Will, what's going to happen to you? You're going to warm up. And so now it's going to be warm. And so that's a feedback loop. So we have several different types of feedback loop. Let's look at the negative feedback loop. All right, we just talked about it. And the important thing about this definition, and the way students often get trapped with this concept, or they can't think past it, is they think of the cultural definition of negative. Negative in culture means bad. In science, it means it stops. A negative reaction means something that's stopped in science. In a cultural way, a negative reaction is, damn it! You know, that's a negative reaction. Right? Negative reaction is that kind of thing. All right, so negative feedback is when, let's go back to our feedback definition, is a circular process in which the output serves as an input to that same system. Going to the definition of negative feedback right here, find lots of stuff. This is a stabilizing system. So it moves in one direction. The input, cold, being cold, creates an output that makes it warm. It gets the system back to normal, to stability, to equilibrium. All right? So negative stops a reaction, moves it back to equilibrium, to normal setting. Same thing with overheating. So if you start to get too hot, what does your body do? You sweat. Your body then cools down, and you stop sweating, and you're back to equilibrium. Really easy. So negative feedbacks reset the system back to normal. Stabilize.
So
Good?
negative feedback loop for stabilizers?
Stabilizes. Stabilizes. Still working. Good. Stabilizes. Your brain does this all the time. Like you might get information right now that your bladder is full. So you're going to get that need to pee. The only way you deal with that is you'll pee, and then your body stabilizes. Input, output. Let's talk about a different type of feedback loop. Positive feedback loop. Doesn't mean it's good, it just means that it keeps it moving towards destabilization. Keeps the inputs and the outputs becoming inputs, keeps that moving towards an extreme. Okay? A great example is with climate change, with melting sea ice. It is a positive feedback loop. Doesn't mean it's good. We're not putting a value on it. We're describing the movement of the loop. It keeps it moving. So let's take a look at it. All right, here's sea ice up in the North Pole. Ice is covered. Santa Claus's village is on the ice. You know he's going to die eventually. How are you going to tell your children about Santa Claus? Oh well. It doesn't matter. Doesn't it? So here's the sea ice. It's staying there when it has snow and ice on there. The albedo, its ability to reflect light away before its wavelength changes, is important. If the wavelength gets absorbed, it will change its wavelength into heat, into infrared wavelengths. And this is a physical science thing. We don't have to memorize that. But we know that more ice, more white-colored stuff reflects and reduces heat. However, as soon as we put a dark object in the middle of that white space, it will start to change the light into heat and heat up the area around it, melting any ice nearby, and thus increasing more surface area to heat up. Then the light is still striking it, heating up more and more, because it's melting more and more. There's less to reflect, it gets warmer. Less to reflect, keeps getting warmer. It keeps moving towards that extreme of all gone. We will be able to see this and measure this when winter comes on the turf field. Snow will fall. It'll land on that turf field. The surface of the turf field is black and green, dark colors. Maybe we'll do a pattern of footprints. We'll measure it, measure the temperature, and in a couple days we'll see that will exponentially start to grow in the melted zone, just like what's happening in the North Pole. So it keeps moving. It's a positive feedback
So it's constantly moving, no?
towards an extreme, toward destabilization, maybe.
So positive feedback loop is basically bad in a way?
Let's not even go to that qualification because it can make it confusing. Because who's it bad for? It's bad for, human life on the planet eventually, in this case. But other versions of it, like exponential, actually all of them are pretty bad, aren't they? Spread of cancer, can't think of positive for that. But really, I don't want you to get too confused with is it good or bad, but that's moving towards the extreme. And so the question is, how do you stop these positive feedback loops once they get going? So let's think about this one. So what is the input that is causing this to accelerate and keep moving towards an extreme?
Sun.
Heat. So it's not the sun. The sun hasn't changed. What has changed? What temperature?
Temperature
The
of the
water.
surface.
Surface temperature or water surface temperature is now changing light into more heat. So we have to somehow reduce that. When we think of it as a climate issue, I don't know how we reduce that. The issue that started it was that the atmosphere was warm. But maybe we reduce CO2 in the atmosphere. It'll take 100 years. Or we can move the planet. I think that's what your class talked about last year, move the planet a little bit.
That would be a good call.
Yeah, just a couple of nuclear explosions, put us out our orbit a little wider. All right, let's review now. So we have positive, negative feedback loops, multiple choice question. That was kind of new. What else is in this chapter that we haven't covered that you think I'm going to talk about? Let's take a look. Environmental systems and their services. Let's see, we have
Is there anything that we didn't talk about that's gonna be on there?
well, here's some terms. Homeostasis, dynamic equilibrium.
Or that's- yeah. So like we should expect everything from these two, PDFs?
I'll tell you what's not on here, on the test.
Okay.
The landscape ecology stuff. None of that's on there. We're not,
What's that stuff?
don't worry about it, we don't even know it. Don't worry about it. It's part of the chapter, it's about GIS mapping and that kind of stuff, and we'll get into that, but.
So like
it's not-
community ecology and that's like not on there?
Community ecology, that whole chapter 4, yes.
Okay.
Yeah, we'll review that, we will, but I just wanna go over 5. I mean, the rest of it's like the spheres, lithosphere, atmosphere, hydrosphere, we talked about that. You can get that in a multiple choice stuff, the way energy moves and the way nutrients move. Energy is a one-way direction, rule of 10, remember? You'll have that kind of question again. Biomass pyramid, why is the top carnivore getting so little energy? Remember why?
Oh, because it's 90% lost.
Right, we're using it up as heat. The energy's transforming and is no longer available. And it's not recycled. It flows, it keeps coming in every day. Without the sun, we don't exist. That's why so many religions worship it. The other big thing is GPP, NPP, RL. Those worksheets, I haven't returned to you, sorry. I need to. There's copies of that worksheet and the topics page. You can look at those definitions again. Since I haven't returned them to you, do you feel like it's fair that I evaluate you
No.
on a test? Well, it's just no. What else? Anybody else agree with her?
I like where Molly says that.
It'd be nice to have it back before so you can review it.
So, okay, I'll save it for the final exam. But
Will we have
I
to-
might ask you what NPP is.
will we have to do any math on it?
Math?
The calculations?
You will have to do biodiversity index
Will you
on
give
this
us-
test and on the final.
Will you give us the formula?
You have the formula. You have it in your blogs, every single one of you. I have looked at blogs, made sure that they have stuff, and now I'm going through the fine grading perspective. Good job. Okay? So net primary productivity, just know the definition. Macronutrients, hypoxic zones, eutrophication, no landscape ecology. The other one that we haven't talked about that's on here is, well, they got these biogeochemical cycles. You should know water cycle, carbon cycle really well. You should be able to do phosphate and nitrates, from a multiple choice standing.
Is this tomorrow or is it Thursday?
Yeah, it's the next class.
Well,
Thursday. And that's it. I thought there was one more thing on there about, I guess the session is in the other chapter. So about the
Yes,
other
it's
chapter.
in chapter 4.
Yeah. It's the session we haven't talked about. There it is.
Did I ever talk about that?
Briefly. And so I want to give you a chance to ask clarifying questions about it. It's been a while since you've had any information on secession, since your last biology class. So there's two types of succession, primary and secondary succession. What's the difference? You know it from memory, Ben? Ben knows. Okay, good. Hold it there. I'll let you fill it in. Does anybody else know the difference between primary and secondary succession? Chris thinks he knows.
Is primary like when it pretty much is starting over with like specific like pioneer species that have to, you're starting from almost nothing?
Okay. Ben, what are those pioneer species?
Lichen,
Yes. And,
I don't know what the
good. What is the point of primary succession? It's supposed to be, there's a function. Here it is, right here. This is primary succession. What's the point? What's gonna happen here?
It's gonna get bigger.
I heard somebody talking about, I couldn't hear what you were saying. Who was that?
Said it was gonna grow.
Oh. What is gonna grow? Populations of
The plants.
producers, of plants. What do they need in order to grow?
Water.
What?
Water.
Sunlight, yes. What else?
Water.
Water.
Soil. Where's the soil in this photo?
Not there.
It's not there. Primary succession is about building the soil. How does a pioneer species like this one in the picture make soil?
It dies, decomposes.
By dying it does it. Yes, what else?
Breaks down the rock.
It helps crack rocks apart little bit by bit. Those little particles collect into these little nooks and crannies. The new plant takes hold, continues the process. We have a feedback loop starting, right? The input of a plant creates a little bit of soil. More soil creates more plant life, more diversity, boom, biome. We've done it. So what the heck is secondary succession? If primary succession is taking a place that doesn't have soil, like this lava field, and making soil so plant life can move in and become a diverse, oh yeah, what is secondary succession?
Using the soil. Cycle.
It's the full cycle? No, that's ecological
Yeah,
succession.
like-
You're close though. Try to get that.
Like an evergreen tree, or a tree that sheds leaves and then.
Is it using the
Cool.
soil to create? Like,
No.
When there is soil already.
The soil's gonna stay from this point on. Whenever the soil's destroyed, there's no soil, we're back to primary succession. Secondary succession is when a disturbance occurs in the forest. There's a disturbance in the forest. Kind of like a disturbance in the forest. Something is disrupted the forest.
like a flood.
Like a fire, a flood, a hurricane, an ice storm, Joey's logging operation. Those things are disturbances. And then what happens next is secondary succession. So let's take a look at that, see if I have a picture.
So it like reacts to what happens.
It's the reaction, right. Right here. Communities respond to a disturbance in various ways. So we have natural disturbances and cultural disturbances. An example of a cultural disturbance would be,
Logging.
what did you say? Logging, yes. For some reason I thought he said laundry. I was like, what else besides logging? Cultural disturbance. I said logging earlier, so something different. Cultural, yeah. Human cause.
I guess a human could start a fire.
A human could start a fire.
Buildings.
Paving it and putting the building down. Absolutely. That's a disturbance. Any others? We mow the lawns, right? That's a disturbance all the time. We keep it at a certain successional stage. So when we have a disturbance, they react to the disturbance or they resist to the disturbance. That's this term resilience, is how it responds to it. They're always moving towards their climax for the biome. So if I disrupted a rainforest, I cut down a classroom-sized acre, let's say this is an acre, I cut it down in the jungle rainforest, there will be a predictable pattern of the plant community moving into that space in a certain amount of time, and what would it eventually turn it into?
Back to rainforest.
Back to its biome rainforest. It won't turn into grassland and remain grassland. We'll go through stages, predictable stages based on the biome. And so that's this picture here. So this is a New England deciduous coniferous forest. So move through stages, predictable stages over time. The rates of time and this change is all dependent upon sunlight, rain, and the climate and all this stuff remaining the same. If I disrupted it, like let's say I did a controlled burn on the saplings and poplar trees right there, that third stage, then what's going to happen to that space? What's going to be the first step? Grasses, herbs, and forms, then shrubs again, then this, then pines, and right? So if I gave you an image similar to this, and I said which stage I disrupted it at, you should be able to say what will happen next. Is that fair?
Yeah.
Will we be giving examples or we just have to name?
I'll probably give you
Does it always just go back to the first stage?
unless the soil's destroyed. If I destroy the soil, how can I destroy soil? Naturally and culturally. Let's do natural first. How?
Take it, throw it away.
So
That's natural?
Flood.
Let's start with natural. How do I destroy the soil?
Erosion.
You can flood it and it's now all underwater.
Volcano.
That'll stop it forever.
Or you
Good.
take it away,
And we'll lift up all the soil, move it away. What's left over?
the rock.
The bedrock. Okay, good. So a flood or a landslide could do that. What else could do that? Reset the soil.
Volcanic eruption.
Who what?
Volcanic.
Yeah, so you have a layer of molten lava, cools, now you have basalt. Yes, those all work. Cultural way. How do we culturally remove the soil? Besides using a spoon and throwing it over your shoulder like that.
Pave over it.
Pave it. Yeah, there's a parking lot is primary succession again. And you've seen it. You'll see a crack in the pavement and one little flower coming down there, like, damn, no flower. It's just nature doing its thing. Succession. What's another cultural one besides a parking lot? Or a building?
fire.
Fire caused by people will destroy the soil.
You could-
Turns what?
Yeah, to turn the flip, yeah, you're right.
Soil will remain.
Alan, you can overuse it, like plant too much or something like that.
Farm it too much so that all the nutrients are gone out of it, so it's desertification.
Yeah.
So plants are still gonna start to come back over time, just not in a way that's useful for agriculture. The soil's still there,
Okay.
so that's a good try.
Melt it.
Think. Melt the soil.
Yeah.
Yeah, you would have to incinerate the soil pretty bad to destroy it. It'd have to be a nuclear explosion.
Yeah,
Yeah,
that would do it.
yeah, you got it, good answer. Okay, so you got an idea. So review, study, work together. Remember chapter 4 is on there. It's multiple choice, biomass pyramids, web stuff.
It's raining.
So we're doing no essay.
That's what I've heard from you guys. No essay, right? Fair enough. I love it. I like it. Good. Save it for the final.
Why does it rain every 6 months?
I don't know.
Literally every day.
Ask somebody who drives a car.
You drive a car, huh?
Oh yeah, sorry, I changed the climate. I changed it.
Thank you, Ron. Thank you.
That is the predicted mode of climate change in New England, more rain. 70+% chance of more rain. Just hope it doesn't happen when you want to ski. You're
Yeah.
gonna get nothing but ice.
That's good though.
Ice is good?
It's fast.
It's fast, oh yeah.
Freaking Easter.
Oh, yeah, weirdos.
Yeah. Thanks for paying attention. And that concludes today's class.